So here I just want to go over the theory for chapter 27, starting with the electromotive force. So it's also known as the EMF or just E, and it's not a force, it's just the maximum possible voltage the battery can provide between its terminals. So ideally, delta V battery is equal to E, but in real life, the delta V battery is normally less than E. And that is because it has some internal resistance R. We can picture this by drawing this rectangle here. This is our electromotive force. And then here we have some internal resistance R. Now delta V battery is going to be the potential difference between this point here and this point here. And we know that that is going to be equal to E, which is providing us our potential, minus I times R, which is reducing our potential. So then from A to B, we have an increase in potential. C to D, we have a decrease in potential. But then from E to F, we also have a decrease in potential that is equal to I times R. Right, so that's here. And we know that I times R, this potential difference, has to be equal to the potential difference between these 2 points. So delta V battery is equal to I times R. Combining these together, we see that E is equal to I capital R plus I little r. If we just multiply this by I, we get this. I squared capital R plus I squared little r. Now, this is the power. So this is the total power provided by our EMF. And we see that it is delivered to 2 sources. So the power generated here is delivered to this resistor and this resistor. Now next, we're going to start talking about resistors in series and resistors in parallel. So here we have current I1 going through this resistor and current I2 going through this resistor. We do know that when they're in series, I is the same everywhere. So I1 is equal to I2 is equal to I, it's the same. We also know that R1 and R2 have the same amount of charge Q going through them. So there's a certain amount of charge going through this one, same amount going through this one. The charge doesn't magically disappear. What is different, however, is the potential differences across them. So there's a potential drop here and a potential drop here. We don't necessarily know what they are, but we know that when we add them up, delta V1 plus delta V2, we get delta V here, because the power here gets given to this one and to this one here. So delta V is equal to I1 R1 plus I2 R2. Essentially what we've done here is reduce this down to one equivalent resistor here. And we said that, well, we know that the potential difference here is equal to the potential difference here. If we write that out, we have delta V1 is I1 R1, delta V2 I2 R2. We know that they're the same. I take that out, I R1 plus R2. So here we know that this is IR equivalent. So the delta V across here is equal to IR equivalent is equal to I and then R1 plus R2, right? Because this is literally taking this, looking at this, and saying, well, that is our equivalent. So when we add up our resistors when they're in series, we just add them up like this. On the other hand, when things are in parallel, we know that for them to be in parallel, we can draw a line connecting them like this without going through any battery or capacitor. We know that the potential across R2 is the same as the potential across R1, which is the same as this potential. So delta VR1 is equal to delta V2 is equal to delta V. The current, however, going through R2 is not the same as the one going through R1. So what we see here is that the incoming current gets split up. Some of it goes here, some of it goes here. I is equal to I1 plus R2. I is equal to I1 plus I2. Using Ohm's law, we have delta V1 divided by R1 and delta V2 divided by R2. If we were to combine these into an equivalent resistor, we would say that, that's equal to delta V, because there's a certain potential here that we already know, divided by R equivalent, and that is going to be equal to delta V, and then 1 plus R1. It's literally just this equation here, 1 divided by R1 plus 1 divided by R2. That means that 1 over R equivalent is equal to 1 over R1 plus 1 over R2. We have already seen this before, but kind of in the opposite way. So remember when we had our capacitors, when they were in parallel, we actually had C is equal to C1 plus C2, right? That's different than this. They're kind of the opposite. Now, sometimes it's going to be really hard to reduce your circuits down to a single resistor. So what you're going to use are called Kirchhoff's rules. The first one is called the junction rule, and it says that at any junction, the sum of the currents is 0. So what that means is, let's say you have this junction here, right there. You have a certain amount of current coming in, and that has to be equal to the amount of current going out. So whenever the current's going in, we say it's positive. So this is 1, 2, 3, 4. Current 1 is equal to what's going out, I2, I3, and I4. If we were to put them all onto one side, we would say that I1 minus I2 minus I3 minus I4 is equal to 0. And that is Kirchhoff's junction rule. So what's coming in has to go out. We also have Kirchhoff's loop rule, which says that the sum of the potential difference across all the elements on a closed loop is 0. So here, let's say we have our battery, and then we have 2 resistors. We have a voltage gain here, so plus delta V. We have a drop here, and we have a drop here. So whenever we do the loop, the gain has to be equal to the loss. Right, so then delta V minus delta V1 minus delta V2 is equal to 0. And that is all that rule is saying. I'm going to do a second video where I'm going to talk about RC circuits.